So, from the University of Queensland, I'm a research student. My name is Philip Dyer. I'm on a quest to understand patterns of biodiversity in our oceans. How are the species and communities distributed across the globe? Now, to understand that, I've got a number of tools available to me. There's a surprising amount of public data available on biology and on the environment as well on a global scale. I also have access to a lot of private data through my collaborations and my supervisors. And I have a supercomputing cluster. Over 1,000 cores, 13 terabytes of RAM. It's going to be good fun. And don't forget. Now, again, why R? Well, in my case, packages. Anytime someone sort of says, which language should I be using for this particular project? The first answer is, well, which one has the libraries you need? Which one has the packages you need? I can sit within R and pull in public environmental data, public biological data, get every single species and community modeling technique I could find in the literature has an R implementation. That's pretty impressive. And that's on top of all the statistical analysis model, of the models I can do, the plotting, and publishing to HTML, PDF, Word, all within R. Don't have to leave R, which is fantastic. Well, what more could I ask for? Speed. I've got a supercomputing cluster. I mentioned that before. So this is all about ways I've tried to unlock more from R when I've got access to more cores than I can use. So the first thing is, you've got more cores, you want to go parallel. Now, one of the great things about going parallel is that everyone these days has at least 2 cores in their laptop, usually 4 to 8 in their desktop. So you don't even need a computing cluster to make use of these techniques. The packages that, and in R, I've had a little work in C and some of those more low-level languages. Going parallel in a low-level language is hard. In R, it's so easy, you forget how easy it is. There's 3 packages I'd have a look at if you're interested in going in parallel, and really which one you choose depends on the code you've already written. So the parallel package comes with base R, and to jump into parallel with the parallel package, you just change your lapply functions and those other apply functions into a par lapply, and you're done. Oh, you have to tell it how many cores you want it to use as well. So it doesn't take much. Almost as easy is the for each package, which I actually recommend is a really useful way of doing for loops anyway, and the do parallel backend. Again, you tell it how many cores you want, you replace your do with do par, and you're in parallel again. Like, you haven't even changed a whole line of code here. The other interesting one is future. If your problem doesn't really fit into a looping structure, the future package allows you to just spit off any line of code, any function into a background process without really having to think about it. These the percent signs on the assignment operator means just start running this, and when I need the results later, I'll ask you. And it just lets you get back on with whatever else you want to do, runs it in the background, and then when you finally actually need the results, either gives them to you if they're ready, or just blocks if it's not. I've been using most of the for each package at the moment because a lot of what I'm doing is embarrassingly parallel. And here's an example. How many communities am I seeing is the data suggesting there might be in the environment? So I run across test either from 2 to 20 different numbers of groups and look at the relative performance of each group as in terms of Bayesian information criteria. And this chart here, you can probably think of it as a scree chart if you haven't seen them before, suggests that about 5 to 7 groups is appropriate. And if you look at the map that generates around Australia, we do see some biologically meaningful clustering going on. There's a sort of a north-south axis. As you get colder, the species you find changes. Now, going in parallel is great, but sometimes you can't just split your problem up into smaller and smaller pieces. And you need to start with better algorithms. And in this case, one place to start, because it is a hard problem in general, is with Data.table. So I've made good use of Data.table because it's a data frame enhancement that adds a ton of memory efficiency. It's much faster. It's quite flexible. You can do a lot of statistical analysis on your data frames as well. And it provides a lot of supporting functions like an extremely fast CSV reader. And in my case, I needed it for this transpose function, which I'll explain in just a moment. Word of caution though, if you're wanting to go down the Data.table route, the syntax is unique to Data.table. I haven't seen anything quite like it before, but it's similar enough to the data frame syntax that you'll get some strange bugs if you forget to load the data table package into your workspace. So in my case, I had 220,000 rows, 3,000 columns, and I needed to transpose it. So I got a data table. I didn't even actually need a supercomputing cluster for this one. Data table made it efficient enough to run on my laptop. In contrast, the built-in T function crashes R. Doesn't even complain about memory, it just crashes. So, making your code run faster if you've got a supercomputer, running it in parallel, running it on data table for the really hard problems, well, that's great. We're flying along, but out in the high seas, you see things. And you're not even sure if you saw it yourself. How do I go back and convince everyone else that I've got some real results, that I actually saw something in my data? Well, that's where reproducibility comes in. We want to be able to analyze the chain of logic from data to results and do it in a way that we can repeat it if we need to, and we can defend it if someone wants to have a look at it. The first thing that came to mind when I started looking into reproducibility was package managers. And I've found they don't cover enough, they don't fix enough of the problem for me to actually using them at the moment. Now, they have their place. We often have the opposite problem where I have too many computers all to myself. And it will help you keep your packages in check, but only your package versions. It won't help with your R version, it won't help with your operating system, and it won't help with the libraries behind your code that packages are talking to. So package management alone won't fix your reproducibility problems. But if you're interested, have a look at PackRat and Checkpoint, depending on your use case. So what I find much more helpful is R markdown. And R markdown fixes this issue of reproducibility. So scripts tweaking and a disorganized file system. Where did I get my plot from? Well, I had a script for that. Where did I... I'll get back to you next week once I've found it. Or I had this great plot, and I generated by testing, I was changing parameters. I got 100 plots, and one of them worked. And I just need to now add a title to the axis or something like that, or just change the color scheme. Wait, which parameter set did I use to get that plot? So this is where, if you're at the Workflow R presentation yesterday, that was an entire talk about exactly how to use R markdown to improve your reproducibility. R markdown looks like this. If you haven't seen it before, it's pretty easy to get started. All you can ignore the front matter if you're using RStudio. It gives it to you for free. On your code goes into little blocks with backticks, and everything else is just plain text that will appear in your final document. And what I find I'm using R markdown the most as a way of wrapping up my code, my results, and any comments I've made all into one output file. So now my figures and the code that generated those figures are all in the same place. I can't lose them without losing everything at the same time. And then I just have to go back and reproduce it anyway. So, and the way you can get that easily inside R is to use the R markdown render command. And then you have to give it a whole file at once, which makes a big difference when you're in a supercomputer and you can't use it interactively, because it forces you to think about, this script is going to run from the top to the bottom, and I need it to all work all at once. I can't change things or modify things on the fly to get the results I need. But that means that your output file is a real snapshot of your work. So I've used a little trick here in the output file command where whatever output file I want is date stamped. So I don't accidentally overwrite old results, and I can kind of have a record of what I've done as I go. And I can, if you want to see, for those who haven't used R markdown and rendered it out to a file before, it's quite nice how the code you started with, which wasn't too bad, can come up looking like a website with results, headers, text, and plots all in place as well. Now, I mentioned package managers are not particularly helpful for figuring out your system state. So I've included in my R markdown files a couple of lines of code that just record it for me. If I ever need to know what my system state was, what version of R I was using, I go look at it. It doesn't magically make my system go back to that state, but that was always going to be hard work anyway. But at least I know what I'm aiming for. So Now, we're on the supercomputer. We've got these R markdown files generating results all stitched together for us, which is great. Now, I just feel there's a few more things missing. Like, you know, sometimes, even with a supercomputer, even with parallel processing, this is still me sometimes. And, you know, it gets boring after about a day or two. It's good fun to take a holiday sometimes, but there's a limit. So, this is where caching comes into play. When we talk about reproducibility before, and in particular with R markdown files, it's pretty obvious to everyone that you need to save your results. You need to have something you can walk around and show people. If you fit a model, often you'll want to save the results too so that you can come back to it later, reuse things. Caching really comes into play when you're not sure if something is even a result, you're not sure how often you're going to use it, but it would save you a lot of time if you didn't have to keep recalculating it. And essentially the idea is, here's my object or my line of code or my function, and if I've run it already, don't rerun it, just give me the result. Store the result, and if I haven't run it before, go do the processing, I'll wait, and save it for me in a place I can easily get back to it later without having to think about it too much. So there's a bit of a spectrum of caching packages out there. If you've got chunks of code that you're interested in caching, the R markdown actually has some built-in caching functions there. The rcache package will do that quite nicely, so that your functions, if you're using the same functions a lot, you get results much faster. And on the other end of the spectrum, looking at objects in your workspace, I find the saw package and the Archivist package have been quite useful for taking care of intermediate results. You can also roll your own if you're really feeling brave. And so in the case of the Archivist package, I like it because I do some work on the supercomputing cluster. I get some models fitted or get some results generated or transform a table in a particular way. And then I'll go and save it into my Archivist repository. And that means it's all in one place. And it gives it a unique hash. Each object you put into the repository has a unique hash. And you can pull it back out again later with that unique hash. So there's a little bit of note keeping I have to have in my lab book where I remember which hash goes with which object. But once I know which hash is associated with a particular model of my species and environment, I don't have to worry about whether I tweak some code, changed the model, overwrote a file, and got some different results, because if the model had changed for any reason at all, it would get a new hash. So I can now, in the future, specify that hash and get exactly the model I want. So that it's sort of in the middle of caching and storing results there. And when I'm working on the supercomputer, that comes in quite handy because I can use those hashes as parameters. And I can also see then exactly which version of my model, which data, whether perhaps I change the number of trees when I was fitting my model, my random forest, it will change the hash, and then I can then track exactly which version I'm using. And last of all, the one thing that really finally brings it all together when you're working on a supercomputing cluster is the concept, the mindset of doing things as batches, working in batch jobs. And the cluster I have access to is a queuing system. You say, I would like to run this, please. It says, thank you very much. I'll tell you when I'm ready to start. Now, if I wanted to use something like RStudio server, which is interactive, I don't know when it's going to say you're ready to start, and I don't know how long I'm going to need it for. So if I can specify up front, give it a job, do this, come back in a week's time, it'll say here's the results. That's much, much more efficient way of working on a supercomputing cluster. And to play nice with all those other users, that's really the only fair way to do it. So the mindset changes from the interactive style of R, where I go in, I run some lines of code, I check the results, I run a few more lines of code, I check the results, I generate a few plots, into, here's my job. I've got it's an entire R script from start to finish. It has to do everything inside that script. I send it off to the computer, and then I can send a whole lot off to the computer, and come back later, pick up the results. So this combines really nicely with R markdown and that R render function. So, and the reason it's so easy to use in batch functions is the R script file and a bit of command line processing on your computer. With R markdown, you can actually set up parameters. set up a few details, put into a script, and that's enough to send off to the supercomputer and say, give me my results in however long it takes. Again, I've specified the output file name to, I think if I push control it makes it mouse. Yes, so the output file name here I've specified as part of the command line, and it's going to date stamp it for me too, so I can always know exactly which result. I don't overwrite results accidentally. Now, using this power, using the supercomputer, I've been able to do analysis around Australia for now, and work up to, and I'm continuing to work up to global analysis. And we can look at, and so my R markdown files, I try to make sure everything I can get into them is there. So this should be a complete summary of what I tried to do every time. So I've got the parameters I sent in, which models, you'll see a number of hashes there, so I've specified exactly which models I want to use. I even recorded which Git branch I'm using, because I do also use Git, but I won't talk about that today. Some other general parameters in the setting up my background, my parallel processing, whether I'm caching, how I'm caching things, and you can see a number of, and so you can get results like this one here, which shows you trends in biodiversity around Australia. So if two points are a similar color, we expect the biology in those areas to be kind of the same. And the particular technique I'm using is quite interesting because it allows you to use information from multiple unrelated surveys. So this picture here makes use of information from tiny microscopic copepods and as well as large commercially fished species. And that's mixed together into the same data, telling us that around the coastlines you get certain effects. As you move from north to south, you get certain effects. And the clustered image I showed you before brings that all together and tries to find predictable patterns that managers could use when they're trying to decide where they should put protected areas or not, and where they should focus their efforts. So if you can make use of, so if someone gives you a supercomputer or even just a multi-core desktop, here's a whole lot of little techniques you can make use of to unlock the power of supercomputing and R.